In this lesson, we introduce Euler Totient functions and prove Euler Totient theorem and show how RSA utilize Euler Totient theorem and generate public key and private key. We prove why when we apply RSA cipher C, which is encrypted with public key E, to the power of its private key, we will recover the plaintext. Euler Totient functions phi of n is the number of positive integer less than n and relative prime to n. Let's carry out some exercise to compute phi of 37 and phi of 35. 37 is a prime number. So by definition, any integer from 1 to 37 minus 1, 36 are relative prime of 37. And based on that definition, there are totally 37 of them. Therefore, phi of 37, or Totient function of 37, is equal to 36. To determine phi of 35, we list all the positive relative prime number less than 35. It is 1, 2, 3, 4, 5, 6, 8, 9, and so on until 33, as shown in the screen here. And actually, there are 24 of these numbers. And therefore, phi of 35, the Totient function of 35 is equal to 24. Next time, we'll show how to compute phi of 35 much faster. Okay, here we show some Totient function property. 1, if P is a prime, then phi P equal to P minus 1. 2, for n equal to P times Q, where P and Q are prime number, and P doesn't equal to Q. Now we have the phi of n will be equal to phi of P times Q, and is equal to phi P times phi Q. And we replacing phi P with P minus 1, we replacing phi Q with Q minus 1, therefore this equation is equal to P minus 1 times Q minus 1. So now let's provide the proof. Let set A to be 1, 2, 3, up to P minus 1 as a set. In set A, the numbers that are not relative prime of n are those with factor P, or they have factor of Q. And for those with factor P, they are P, 2P, 3P, all the way to Q minus 1P. For those factor of Q, they are Q, 2Q, 3Q, all the way to P minus 1Q. Take them out of the set A, we will find out the number of the remainder set is phi n. So phi of n is equal to PQ minus P times Q minus 1 and minus the factor of Q and Q, therefore is square parenthesis Q minus 1 plus P minus 1. Okay? And therefore, you simplify the formula is equal to PQ minus P plus Q plus 1. Okay, so that equal to P minus 1 times Q minus 1. And that is happen to be phi P times phi Q. Now let's look at the example. Phi of 35 is equal to phi 7 times phi 5, right? And with the above formula, we can substitute phi 7 with 7 minus 1. Phi of 5 we can replace it with phi minus 1, and therefore it is 6 times 4 is 24. It can be calculated very quickly without having to enumerate through all these relative prime. Okay. Same thing for phi to the power of 21. We can factor out 21 with 7 times 3. Therefore, phi of 21 is equal to phi of 7 times phi of 3. Phi of 7 is 7 minus 1. 3 is a prime number, therefore is 3 minus 1 for the phi of 3. So 7 times 1 minus 1 is 6. 3 minus 1 is 2. 6 times 2 is 12. So you will compute getting this result right away. Here is a Euler Totient theorem. For a and n, that is relative prime. A to the power of phi n is equal to 1 modulo n. So basically say a to the power of phi n and 1, they are congruent modular of n. And let's provide the proof. Case 1 is a degenerate case where the above is true when n is a prime. So since phi of n is equal to n minus 1, and the formula becomes the Fermat-Little theorem, where a to the power of n minus 1 equal and 1 are congruent modulo n. And here we substitute n with a p, basically in the when we present the Fermat-Little theorem. Okay, case 2. Let's prove a generic case where this formula, this Euler Totient theorem, actually true for any integer n. Consider the set. Here the proof is very similar to how Leonhard proved the Fermat-Little theorem. Consider a set R that contains all the positive integers less than n that are relative prime of n. So we have x subscript of 1, x subscript of 2, and so on until x subscript of Totient function of n. And we multiply each element by a, then modulo n, do a modulo n. The result is a set S. So the first term will be a times x sub I more n. The second term will a times x sub 2 modulo n, and so on until the last term is a times x subscript of phi n and modulo n. And so that's a set for S. And we can prove that S is a permutation of all those numbers in R, and based on the following two reasons. The first one, A and X are relative prime to n, and therefore we can derive that A times x sub I is a relative prime to n. All the S set numbers are integer less than n and relative prime of n. Since there is no duplicate in S, the same proof we can prove using the same proof by contradiction as in Fermat-Little theorems, where if A times x sub I more n is equal to x sub j mod n, then x sub j is equal to x sub I. And but at the same time, x sub I and x sub j are a number in R, And since no element in R are duplicate, the above proved to be true. Basically saying the two terms we just talked about in set S, they cannot be equal. Okay, so that concludes the proof. Here we show the step 4 of Euler-Totient theorem. Since S and R contain the same several number, what we can do is multiply all the term in S. That should be equal to multiply result of all the term in R. And you can see the first equation here. And then we take the modular n on both sides of the equations. We now have the equal sign becomes the congruent modular operator. Second equation, you can see we take all the a in the left-hand side term out. And since this is a multiplication operator, they are 1 to 5 of n. Therefore, they are altogether, they are 5n of a. So it becomes a to the power of 5n as a term outside of the operator, with using the orange block to make it easier for you to understand there. The third one, we cancel out the term. The term is happen to be the multiplicator or the term of x sub I, where I equal 1 to all the way to 5n. And since both sides in the third equation has the same term, we can cancel them out, divide them based on that term. So we will get the final result, that is the final term in the fourth equation, with a to the power of 5n and 1 are congruent modular n. And that happened to be exactly the Euler-Totient theorem. And this concludes the proof. Leonhardt used the same proving technique of his Fermat-Little theorem. But look at here is a much more general case. It's a very intelligent, smart proof. Here, let's apply Euler-Totient theorem with some concrete number. Okay. First, let a equal to 3 and n equal to 10. For Totient function of 10, we can apply Totient function property where if n is a multiple of 2 prime, then the Totient function n is a result of the multiplication of two numbers which are each prime number minus 1, which of each prime minus 1. And this leads to 4. And therefore, the right term is 3 to the power of 4, which is 81. 81, we can calculate that as 8 times 10 plus 1. Here's n is 10, right? Therefore, the remainder is 1. And therefore, we can say 81 and 1 are congruent modular 10. This verifies the formula is indeed correct, right? Same for the other example where a is 2 and n is 11. You can compute, follow the same reasoning.